Hi and welcome everybody to my talk about fault-tolerant software design, or fault tolerance made easy. If you might wonder what this picture is about, there's no deeper meaning in it. I just like the picture, and as the title slide of the DevOps slide deck looked a little bit barren, I put that picture in here. That's all of it. So let's go to the next slide a little bit quickly. My name is Uwe Friedrichsen. My Twitter handle here, yeah, of course, and I'm a fellow of Codecentric, and I don't think I'm going to talk a lot about what I did in the last 30 years and stuff like that and bore you with that stuff. I think we better start up with the presentation itself. So let's start with the core statement of this session. It's all about production. I mean, we're doing Agile for a lot of years meanwhile. At least I hope that all of you are doing that for several years meanwhile. And Agile taught us a lot about that business value is important and that we should better deliver business value. And this is really important, and we have to care about that. And then we're doing a lot of clean code, of course. And clean code taught us that we should write readable code, tested code, so actually maintainable code, code which is easy to change, which is also important. But all of that doesn't help us at all if the application we've been writing isn't running in production. And that's what this statement is about. We are not writing code for ourselves. We're also not writing code for QA or for our product owners. We are writing code applications to be running in production. And running in production, first of all, means availability. I mean, a system which doesn't run doesn't make any money, of course. And it doesn't satisfy customers, which is also important, because customers are gone then and they're not going to make money anymore, of course. And to deliver high availability, you need resilient applications. Applications which are resilient to all kinds of errors and all kinds of unexpected situations. And the basis for building resilient applications is fault tolerant software design. And now we are back to the title of this talk. I organized this talk by providing you with a few case studies how not to write resilient systems, and then show you a few patterns down to the code level, what you can do about that, how to do that better. And yeah, there are more patterns that I'm going to present to you today to deal with the situations I'm going to sketch now. And there are also, the code isn't actually production ready. I stripped down a few details to make it fit onto the slides and keeping a readable font, of course. But I think it's 80% of the work, and if you're starting with the code example and the patterns here, it will give you a nice head start into writing more resilient applications, into writing better production-ready code. So let's start with the first case study. I mean, I think you probably encountered that situation once in a while. The web server is not responding anymore. So customer's best friend is the hourglass. They're waiting and waiting. Nothing's going to happen. Some guy with a suit and a tie is angry and is calling the admin all the time. Why the heck this freaking application is not responding anymore, and so on. And of course, there's a lot of hectical root cause analysis going on. And you're looking at the web servers, and after a while, what you're going to figure out is all the worker threads are blocked. They're waiting for the application servers. And then, the next step, you're looking at the application servers, and after a while, you figure out quite the same thing. All the worker threads are blocked, and they're waiting for the database. And then when you're going down to the database, what you're going to figure out there is that there's some odd batch job running, which is actually consuming consuming up all the resources available, and database isn't responding anymore. And today, we're not talking about how to fix the database issue. It's a different talk. What I want to talk about is that it's a bad behavior of the web server. I mean, The least thing the web server should do in this situation is that it gives you back some kind of an error page telling you, oh, I've encountered a problem, so please try again in some minutes. Something like that. I mean, that's like standing on the platform and waiting for a train which is not coming. If you're waiting and you don't know if the train's coming or not, you get really upset. If you get this message, train will be delayed for 20 minutes, I mean, you're still not happy, but you can deal with that. You can go down again from the platform, get yourself another copy, or go to the bookshop, or whatever. And that's what the application should do. Or even better, it should make a graceful degradation of service, nice term, which means, for instance, maybe you have all the data of the customer in some caches, and the only thing you can't do at that moment is that you can't place any new orders or whatever kind of modifying actions. So that whenever he wants to see the status of what's going on and so on, you can still deliver all that to him. And only if he wants to place an order, you say, at the moment, we can't place any orders, come back later. Or you store it in some interim storage, or whatever kind. But the problem is, you can't do any of that because you don't have any control anymore. All your threads are blocked. They're waiting for this other application to come back. And that's where the first pattern comes in handy. It's a very simple one, timeouts. I mean, timeouts give you back control to react, to do some action if something goes wrong. How can we implement those timeouts? I mean, let's start with the easiest way to implement that. There are a lot of methods in the Java standard library who provide you several forms of how you can call them. So like the wait, you have one wait, which is blocking, and one wait with a timeout. Or the join, you have one join, which is blocking, and the other join with a timeout. So you better don't use the blocking one, use the one with the timeout. So just waiting for a certain amount of time and then getting back control. But unfortunately, you don't always have this easy way out. So maybe you have some blocking action. I sketched that up here with this my blocking action. What can you do about that? Again, just taking some means from the Java standard library, it's straightforward. You wrap that into a callable. For those of you might not know a callable is the same thing as a runnable, but it can basically return a return value or throw some exceptions which don't go and kill the thread, but which are handed back to you, actually. So, nicer variant of a runnable. And then the only thing you have to do, you have to instantiate an executor service, which is a single-threaded executor service, okay, and then you have to submit your blocking action, and you are waiting for the future to come back. And the future get method, again, has two variants, a blocking one, a non-blocking one. Don't use the blocking one, of course. And here you go again, here's your timeout. Straightforward, not a lot of code to implement that, but you get back control if the other system you're calling isn't going to respond anymore. Or if you're using some other libraries, like, for instance, Guava, you can even make it shorter. Guava delivers you something like a simple time limiter, which gives you a simple call with timeout, which actually internally does the same thing as I sketched before, but even less code to write. So if you're using Guava, why not using that one? And there are other libraries around which provide you with similar means. So writing timeouts to get back control is really easy. So why aren't we using them all the time? And there's one problem with timeouts. What the heck are we going to do if that timeout exception is really going to happen? I mean, that's basically the reason why most of us are not using timeouts, I think. And actually, that's not a fault of the developer sitting in front of his IDE and thinking about, what should I do then? Or let's better use the blocking one because I have no clue what to do if the timeout exception is going to happen. It's a design flaw. your team or your architect, your product owner, whoever is responsible for that, has to sit down and think about what are we going to do in this situation if this service is not going to respond. So let's get a decision about that and then use the timeouts. Straightforward stuff. We're back in control and the calls are going to stop from that pissed manager which doesn't like that his application is not responding anymore. And your customer's a lot more happy also. So how to go on from that one? I mean, let's tune it a little bit. What's a good timeout? Is it a second? Is it 5 seconds? Is it 100 milliseconds? It depends on your use case and the resource you're calling. And so it's a little bit of trial and error to figure out the right timeout. And if you don't have any clue, better make it configurable. So your admin can optimize that at runtime and can figure out the best value. And if you make it configurable, please be so kind and make it configurable dynamically, which means don't let the admin restart the application or make the admin to restart the application to try another timeout value. Use JMX or whatever you are using for making your configuration parameters dynamically changeable. You can even make it better like using self-adapting timeout. So if you have some monitoring around and you measure how long your calls are going to take and stuff like that, then you can deal with some percentile. So let's take the 99.5 percentile, which means that 99.5% of all calls are faster than this value, and everything that's slower, you say, that's probably not going to respond, so that's timeout, or whatever else. And of course, you have to cut that in the limit because the percentiles are going to change if your resource is down, and so it's going to move up automatically. And the last thing to mention is timeouts in Java Enterprise containers. There's always that thing that building your own threads in Java Enterprise containers is forbidden. I'm not sure if that's any more the case. I just read through the whole servlet specification and there wasn't a single word about that you must not use any threads in a web container. I'm not sure about about the EJB container. I haven't used an EJB container for about 8 years meanwhile. And I'm probably never going to use that again, but there are a lot of experts around who can tell you the answer about that. Problem with threads in Java EE containers is that it's twofold. The one thing is many people don't know how to handle threads correctly, and so they make the whole container unstable, and which is the opposite of what we want to achieve. And therefore, if you don't know how to deal with threads correctly, you better don't use them on your own. And the other thing is that the container does make some assumptions about the threads that it has in its hands. So it's things, I belong, I own those threads and I can do with them whatever I do. And if you steal threads from it, it might run into some trouble. But at least I can tell you, we are using our own threads in web containers, actually Tomcat all the time, and it works perfectly fine. But in our current team, we also have a lot of persons who actually know how to deal with threads and how to do with that. Unless you know, it's a little bit more tricky, of course. But it's doable, actually. With Java EE, with EJB containers, ask some other people. Some people told me there are timers around and threads in JPA and that you can use in the JPA adapters and some other stuff. I'm not the expert for that one. But again, here are 3,600 people around, and there's for sure someone who can tell you exactly how to do that, working with timeout there. Okay, so much for timeouts. Now let's go to the next pattern in this situation. I mean, we have those timeouts now, and we regain control. But isn't it a little bit stupid to wait all the time for the timeout to happen if we know that the resource we are trying to access is down? We could do better, and there's a rule of thumb in fault-tolerant software design, which says if you know that you're going to fail, you better fail fast. So come back as soon as possible, because it gives you more time to react on the situation. So don't wait for a long time until you're going to fail, if you can do that better. And that's what the circuit breaker pattern is about. The idea is here, you put kind of a circuit breaker between the client and the resource you're going to access. And you're sending your request, and the circuit breaker keeps track of the status of the resource. If the resource is fine, it lets the request go through and do its work. And otherwise, it just sends back an answer immediately that the resource is not available, so you fail fast. And it's implementing that by using a quite simple state machine. So here's the state machine. It's the original one from the book Release It from Michael Nygaard. I'll come back to that later, to that book. There are lots of implementations around, but this one's straightforward and it's easy to understand. So whenever you start a circuit breaker, it starts in the status closed. So breaker is closed. And if a call comes through there, it says, pass it through, it's fine. And if the call succeeds, I reset my failure counter. On the other hand, if the call fails, I increase my failure counter. And if my failure counter reaches a threshold, a certain threshold I have to configure, it trips the breaker. And tripping the breaker means that it switches the status to open. Now the behavior is different. Whenever a call comes in, it just fails. It just goes back immediately, sending you a response, resource is not available. But we don't want to stay forever in the open state, and therefore, after a certain timeout, we try to reset our breaker. And that's the third state. We're going back to a state called half open. And in half open, the next call is passed through, and you watch the result. If the result is okay, so if the resource is available again, you go back to the closed state. And if it's not okay, if the call still fails, you go back to the open state. I mean, it's quite straightforward. There's no magic in here. How can we implement that? I did a quite simple implementation here to save some slides, a few optimizations in here, but it's basically working. So that's just some initialization stuff. The only thing that's probably interesting here is that I implemented as a wrapper around the access to the resource itself. So it's kind of a decorator pattern or whatever you want to call that. And here's the core access method. At the beginning, state's not open, so we can skip that if, and we go in here and we try to access the resource. And of course, if it succeeds, we call it success and return the result, and if it fails, we call fail, and we hand out the exception for further processing. Success is quite straightforward. I use the reset method here, so I reset my counter, and failure is I increase the counter, and if the counter exceeds a certain threshold, I call trip breaker, which then switches the state, and I just save the time when I trip the breaker for dealing with the timeout later. Let's go back to that slide, to the access. Now I'm state open, and here's one of these optimizations. So to save a few lines in here, I implement it this way that I throw the resource not available exception one time more than I need. Now, I mostly need, but usually that doesn't make a big difference. So I check the timeout and I throw the resource unavailable exception. And checking the timeout is quite straightforward. If timeout is exceeded, then I switch my state to half open, and actually the core implementation here is I change my counter to threshold. So the next call will either go above threshold again or will reset everything. So straightforward implementation. I mean, you can make that a little bit more clean in the design so that the half open state is used correctly and that you don't throw a resource unavailable exception more often than necessary, but that's just a few lines of code. Again, no big deal to implement this. How to go on from here? I mean, the first thing is obvious. We want to make that thread safe. I left that part out just to make the code more clear in here, but that's actually not too hard to implement to make that thread safe. And then you could also try to deal with different failure type. I mean, timeout is not the only situation you might have to deal with. So for instance, you might encounter with some resource some other kinds of errors, error situations like they immediately respond, but they don't give you anything. So you get a blank result, which is also some kind of failure, which you might want to deal with in here. And then tuning circuit breakers is actually the same as with timeouts. So make things configurable if you don't know better, or if you have a good monitoring at hand, you might use that to adapt the counter number, so the threshold, and so for instance, like let's use the average failure rate or something like that. That you know if your counter is going to get bigger than your average failure rate, then you probably have really a problem. So depending on the type of resource you are using. And there are some implementations around. So if you don't want to code that on your own, for instance, I know that Hystrix from Netflix, that library, implements its own circuit breaker, and there are some other implementations around. So Google is your friend, basically. Before you ask how is Hystrix working, I only know that they have that implementation. I haven't worked with that before. So I want to have a deeper look into that, maybe looking if I can replace our own code with that, but haven't done it yet. Okay, let's go to the third pattern here. Third one is fail fast. So the pattern belonging to the rule of thumb. If you know that you're going to fail, you better fail fast. And that's quite straightforward, the idea for this pattern. So your client is going to call some kind of expensive action, which is going to use a lot of resources. Then instead of letting this action run and run and run and run, and at the excess of the last resource, it's going to figure out, oh dear, this last resource isn't available. It's better to check all that stuff quite at the beginning and then to fail immediately instead of letting it run all the way through and doing all that expensive stuff. So if you're going to fail, do it fast. And with the circuit breakers we have at hand, that's really straightforward to implement. So what we're going to do is we set up some kind of fail fast guard. We do that call. And first it checks if all resources are available, and if the resource is available, it forwards to the expensive action, which is then going to use all the resources. And otherwise, we fail immediately. And as I said before, having the circuit breakers at hand, it's straightforward to implement. So the fail fast guard is nothing like a simple method which takes a set of circuit breakers, which are wrapped around our resources, and checks if all of them are closed. And if not, we're sending back some kind of response. Hey, this action, which is going to use all those resources, is probably going to fail. And only thing left over is, if I've got my expensive action here, I've got to call the fail fast guard first before I'm going to execute anything. Again, no magic, simple code, but we're a lot closer to writing a resilient system which is production ready. So we've seen 3 patterns here which help us to deal with timeouts and several kinds of errors when accessing other resources. So let's stick with that for the first case study. Let's move on to the second one. That's what I call the site to successful exception. You maybe know that situation. Let's give you an example for that. So there's this one band, and you always wanted to go to a concert for them, and it's coming on tour. and is giving a concert close to your hometown, and you must go there. You have to. I mean, there's nothing more important in your life than going to this one concert now. And you know when the sales is going to start on the internet, and you've got your cup of coffee ready, you've got your mouse ready, you cleaned your system to have everything running smoothly before, and you're waiting until sales is going to start. And when sales is going to start, you do your click, and you wait. And wait. And you click again. I mean, you know the old pattern. If a system is slow, it's not responding, better reload. Often it makes the system faster. So yeah, you click, and somehow you get through and you get in, but it goes on a bit per bit basis. At least you've got the feeling. So it's coming in slowly, and it's taking forever. And just when you want to go to the checkout and you do your next click, after a while it responds and says, your session timed out. And as you want to start again, you will see the message, concert sold out. Right? You want to kill someone. You're not yet sure whom to kill, but at least kill someone. Or if you're a little bit more peaceful, at least you want to punch someone quite badly. Yeah. And that's okay if you want to do that, because you could have implemented that better on the other side. And there's a lot of patterns for that, but here's one that could especially help in this situation. That's called shed load. I like that one because it's really easy to implement and it gives you a huge effect. The idea is that you have several clients who do too many requests to a server, so that the server goes into a kind of overload situation. And what you're going to do is you put a gatekeeper in front of the server. So there are these too many requests coming in. And on the other hand, you've got a monitor of some kind who is going to monitor the load on the server that all these clients are trying to access. And you request this load data on a periodical basis. And what you're going to do then is, if you've got too much load, you're starting to shed some requests. So you keep the service fine for all the requests which are coming through, and making sure that not too many requests are going to hit the server. So not everybody gets a response, but whoever gets a response gets a fair response, and it's quick enough. So it's not this complete overload situation that your requests are not going to respond anymore at all. How to implement that? Let's start with an easy implementation here again. So I implemented that as a simple servlet filter. So that's just some initialization. Don't bother about the random here. That's just for my shedding strategy because I used a quite simple one. So that's not, and a little bit of boilerplate code here. That's straightforward, so don't care about that. More interesting is this one. That's the filtering itself. First, I try to access the current load of the system. Come back how to do that later. And then I simply decide, should I shed or not? And if I'm going to shed, I just send back some kind of error page with a 503, service unavailable, and maybe a recommendation, try later after a while. So it's all part of the HTTP spec. And otherwise, I'll go on and do the processing. And the should shed is also, here it's just a simple example implementation. What I'm going to do is, if I'm below a certain threshold, I say no, I shouldn't shed, of course. And otherwise, I normalize that load value to a number between 0 or 1, 0 for the just being at the threshold, and 1 having the maximum load. And then I just use that random number to figure out if I get a value below that number that I just calculated. And if yes, if I'm below that, I'm going to shed. Yeah, that's basically it. I mean, it's not the coolest strategy at all, but quite often, at least for stateless servers, that's sufficient, usually. There's one thing about that, or there are several things about this implementation. The first one is that it's not always a good idea to do this check on the server itself. So it's better to check at the periphery, so with a kind of a proxy which is before that server. Some years ago, that was quite a bit of magic. Meanwhile, that's quite straightforward. Just pasted some web page in here which says, hey, I can build my own proxy server, HTTP proxy server with 20 lines of code with Node.js. And yeah, that's straightforward. So it's quite straightforward to implement that with some tools with like Node.js or with Vertex or some other tools to implement some kind of proxy server who's going to do that. And in some situations, even easier if you know that you can handle a certain amount of connections, but no more. Without going to an overload situation, you can even use some kind of a static implementation for that, simply using an Nginx proxy server in front of that, which is using the limit connection module, something like that. I mean, it's not actually the core idea of the pattern, but sometimes it's sufficient and easy to use. So we have a simple load limiter implemented right now. How to go on from that? Yeah, I mean, I had that random shedding strategy. I just showed a random shedding strategy, which might be okay for stateless servers, like if you have a REST server. In the situation of the case study I've described before, you probably have some sessions. So probably you're going to implement some kind of strategy. If you have a started session, you let it go through, but you don't accept any more new sessions if your load is too high. And you could use some kind of nonlinear shedding strategy. So the closer you get to the maximum load, the more you refuse to accept new sessions, stuff like that. And I talked about how to retrieve that load. I mean, it's not a good idea at this situation always to go to a remote system and try to retrieve some load number or something like that. And actually, you don't have to. So how you're going to access any number from remote systems, I don't have to tell you. I mean, that's quite straightforward. But what you're better going to do is that you are using some caches, and you cache that number and update once in a while, either using a separate thread and polling the load once in a while, or a push strategy from the other system, depending on what you're having at hand. And but staying in your local address space while accessing this number here in the filter or in this shedding implementation. And tuning again is straightforward, so I'm not going to repeat all of that. Make it configurable, adopt from historic load patterns, and so on. And of course, there's some other strategies. So shed load is one possible situation. The other one that you quite often have is the share load pattern, which you use from the scale out system. So if your load is going to get too high, you start another node and share the load between the nodes. But this gives you some other issues because that's quite a deal to implement something in a way that it's really in a scale-out fashion, that it really works in a scale-out fashion. And there might be some places where it's more feasible to accept new ones and kill the old requests, not in this situation here, but there are places, and so on. There are a lot of strategies around, but it depends on your certain use case, which one you're going to use. Okay, let's shed load. Again, no magic again. Well, there's another one that I want to show you here, which is deferrable work. Because overload situations are not always just generated by the requests which are coming in, but there might be also some kind of routine work which is going on in the background, and which is also causing some load on the resources you're trying to access online. And what you can see here, these routine work can be some batch jobs that are going on in the background, some maintenance jobs which are cleaning up some things, or some map reduce stuff, or whatever. And what you can see there, if you don't use the deferrable work pattern, is load situation like that. If your load is low, everything's nice. If your online load is getting higher, up to a certain point, it's still nice. But then, if your online load, so your request processing, is getting even higher, you get into an overload situation, even though the requests themselves wouldn't cause that. It's that add-on routine work which is going to cause the overload situation. And maybe that stuff's deferrable. So what we want to have actually is a pattern like that. Here we don't want to do anything, but if we're getting closer to the overload situation, we want to cut down that routine work a bit and make sure that we're not going into the overload area, if possible, which is quite often okay and feasible. How to implement that? So what I did here, I sketched a quite simple batch loop. I mean, real batch frameworks have a little bit more of fancy on there and a lot more of stuff to take care about, but the core logic is the same. I start with some initial state to initialize the batch, and then I process some batch of work, and I update my state all the time. So that's actually, the state is what you use usually in batch frameworks. That's your restart state. So if your batch breaks down, you have to restart the batch. You use that state to find out where to start, where's the restart point to continue the batch. And that's basically the core loop in here. And here's a simple one. So I do something, I do a batch of work, or I just wait. It's straightforward. I mean, I retrieve the load again, and if it's higher than threshold, then I just wait for a certain amount of time, and then I try again. I mean, it's so simple, I almost do not dare to show you that one. But if I don't see that stuff in a lot of code, and that's a problem. I mean, it's so easy, but most people simply don't think about that. That's why I'm showing that. Or the other one, the adaptive one, so I do that main loop again, and I just wait load-based and then do the next piece of, next chunk of work. And wait load-based is then I wait for a certain amount of time, which is dependent on the load I have. Unless I'm higher than a certain, as long as I'm below a certain threshold, I don't wait at all, and otherwise I wait based on how close I am to the maximum load. Again, straightforward strategy. How to go on with that one? The delay strategy. I mean, those two ones were very simple ones, but they're helpful. The first one can make you starve so that nothing's going on. The second one will always do something, but you are having a higher load. So maybe you can implement some other strategy which is going to defer more aggressively if the load gets too high. So if you want to make sure that your quality of service is kept fine for the request processing, some nonlinear delay, whatever. And retrieving load is a different thing here as with the shared load pattern, because right now we are on background jobs, and here we can afford to go out to a remote system all the time. Please use timeouts for going to the remote system, that you're not going to get stuck here again. And retrieve the current load number, because usually processing some chunk of work takes a while. It takes several seconds or even minutes until it's done. And then you can afford that. So you don't have to do this much of elaboration to keep the access to that pattern, to the load number cheap. And tuning, again, is the standard stuff that I told you before, make it configurable, blah, blah. And which is a nice thing here is also for all your batches, please add some kind of a switch for your admins to pause any batch jobs immediately or to stop them immediately in a controlled fashion, because if your framework they're running in is not going to deliver it out of the box, because sometimes it just might need that. That's it. Okay, so much about handling overload situations. Again, there are a lot of more patterns around, but I just wanted to show you some easy ones would give you a nice head start for that. Let's go to the third and the last case study we're having. Assume the following situation. You've got to connect to some kind of external system. And connecting to that basically isn't too hard. But, and testing worked fine and all that. But in production, it turns out that the system is kind of a mean bastard. And what I mean with mean bastard is that sometimes it doesn't respond. But it doesn't give you a straight pattern like you can catch with a circuit breaker, so that it's not going to respond in a line if it's down, or it's always going to respond. It sometimes doesn't respond. You get some queer patterns like it doesn't respond, it responds again, then 3 times it doesn't respond, then 2 times it responds again, and so on and so on and so on. If you would restart that service, usually this effect goes away and it works fine for a while again. So the connection to the service, if you restart the connection. Problem is that restarting the connection is quite expensive, so you would lose a lot of calls and wouldn't be available for a while. And just ignoring it isn't always a solution, because sometimes it recovers from this kind of behaviors and sometimes it just goes worse until almost no call is going through again anymore. And it's quite tricky how to handle that one. So what are you going to do with that? As I said before, the circuit breaker doesn't work exactly because some of the calls are going through and giving you a reasonable response. It might get worse, it might recover. Stupid one. And there's a nice pattern for that one too, which is really easy to implement. That's a leaky bucket pattern. The idea of the leaky bucket pattern is you have a leaky bucket in here. So a bucket with a hole. It's just this figure, therefore leaky bucket. And whenever a call fails, you fill some virtual water into it. And periodically, you leak some water out. There's this tiny hole in the bottom of it. And if the bucket is going to overflow, you know you really have a problem, and you have to do some kind of error handling. So in this situation, restart the connection. So if you don't get too many errors in a certain period of time, everything's fine. You can get some of them. You consider them as transient errors, which is okay then. But if you get too many of them in a certain amount of time, you think you've got a problem, and then you have to do some error handling. Nice thing about the pattern is that the business code over here and the error handling gets separated, which is also another pattern and fault-tolerant software design domain, which says separate the error handling from the business code or from the core logic. And that's a good idea for 2 reasons. One reason is at the place where the error is going to happen, you often don't have enough information at hand to handle that error properly. If you go out to a dedicated error handler, you might have more information and also maybe more time to analyze that error and to take some proper action for that. And the other one is so simple that many of us don't think about that. It makes the code better readable. And this is an easier and better readable code and better understandable code is easier to change because it lowers the probability to introduce new errors when you change the code. And that's also a high value in the domain of fault-tolerant software design, to reduce the probability of introducing error when fixing some other errors. So it's a nice pattern. And the implementation of that is so easy, the core implementation, that I almost do not dare to show you because it's exactly what I told you before. I've got one of those in production and it's working fine. I mean, it's just a bucket and yeah, you give that some kind of initial capacity and yeah, here's some method to drain it down to 0. So if you want to reset that, filling it up, yeah, you increase the level, and if it's higher than the capacity, you say, yeah, now it's overflown, and Otherwise, you're going to leak then here, and yeah, that's basically it. So, really straightforward stuff. Okay. How to optimize that pattern here? First one is, of course, again, you have to make that thread safe. But basically, making it thread safe is quite straightforward. Make some of the variables atomic should work and should be sufficient for most situations. In some other places, you might have to do a little bit more, but basically, that's fine then. Leaking strategies. You have to find a good place where you're going to leak. So either you need another thread which is doing nothing but sleeping for a while, leaking, sleeping for a while, leaking, or maybe you have some other place of code which is executed in a regular manner and you can just put it in there. So if there's some place you know, oh, we're going to hit that every 100 milliseconds or 1 second or whatever amount of time you need, great place to put it. With every nth call, whatever strategy is sufficient for you. And again, the tuning is again quite straightforward. You might use different fill rates for different kind of error situations. You can adopt the counters to some average error rates if you know the numbers. You can make it configurable, blah blah blah. And I think there are some ready-to-use implementations available. I haven't looked for that yet, but Google is your friend, and I'm quite sure that you will find some ready-to-use implementations out there for this pattern too. So you don't have to implement it on yourself, even though it's so simple that probably you can dare to write these 20 lines of code to get the things running and usable. And the last one I want to talk about is the limited retries. So in some situations, you don't have such a mean bastard as I described before. You just have some transient errors to occur so that, you know, once in a while, the call will not succeed. But that's okay. Usually a retry will fix it. So transient network problem or whatever what you want to get across. And so you can make that even easier and implement that just with a simple loop here. As long as you didn't do too many tries, you just retry to do your action. I assume here that it just returns a true if it succeeded and a false if it didn't. So just to make the code more easy to read. And you do a loop around that. And since it's a rule of thumb that usually it's not a good idea to retry more than once before escalating if you have a transient error situation, so either if it's overload or non-accessible resource in that moment, you can write that even easier. So even simpler version of writing that simple line of retry. Yeah. Okay, you can also tweak that a little bit. First thing you have to take care about is that you better use idempotent actions for retrying. I mean, as long as you're in a distributed system, you are no longer in a deterministic system, you're in a probabilistic system. So things have a likelihood to work. It's not sure that they're going to work. And if you're working in a system which have a probabilistic behavior, it's better that you implement all your actions in an idempotent fashion, which means that you can call them more than once and it won't give you some unwanted side effects, but that you can call them as often as you want and the result will always be the same and no additional side effects. And of course, with closures and lambdas, so for instance, if you take Guava, you have them closures in place, or lambdas with Java 8, you can make that even nicer, so encapsulate all these actions and use that stuff. And tuning is, again, the same stuff. I don't going to repeat that. So these were basically the patterns I wanted to show you. I put some stress on using patterns which are really easy to implement and help you to get more resilient systems, which again, in turn, increase the availability. I mean, there are other patterns around which I have to admit, which are mean bastards to implement, which are really, really hard to implement. But again, there are a lot of patterns which are surprisingly easy to implement. These are where the patterns I want to show you. There are also some more patterns which do not fit in here into the case study, which I didn't mention, like something like complete parameter checking, which just says if you have a failure unit, don't only check for timeouts if you call something else, also check everything which is coming in completely if the parameters are fine, are making sense, because that keeps you from propagating errors through the system, which we should do all the time anyway, but which we usually don't do. It's quite straightforward and easy to implement that. Or marked data is another one which is quite straightforward. So if you read some data record and you figure out this one is corrupted, this one is broken, why should everybody else figure that out on its own again? So just put a flag on it, a dirty flag or a corrupted flag on it, and say, and everybody else just sees that flag and just can skip that, so that you're just not going to read that. And then you have some background job which is going to fix that, some maintenance job that's going to read all the corrupted ones and say, oh, what's wrong? And then trying to fix that stuff. It's normal situation in many of scalable distributed systems. You will find in routine audits, which are going to check if your system is still, all the pieces are up and running and doing these maintenance jobs and all that stuff. Not too hard to implement, quite straightforward, but they're all making your system more resilient. And more resilient systems mean higher availability, which means happier customers and more monies. Okay. Well, that's basically the stuff I want to talk about. If you're curious to learn more about writing resilient systems than just a few things I showed you, here is some more further reading. First of all, Michael Nygaard's book, Release It. If you don't know it, get yourself a copy, read it. I mean, I think that's the book that every student after his Computer Science 101 should have to read, because it's all talking about how to write production-ready code. Not more, but not less. That's really a great deal. I love that one. There's another great book from Robert Hanmer, which describes a lot of patterns of fault-tolerant software design, which I think is a book number 4 of this POSA series. And there's a nice pattern from James Hamilton, who was in charge for designing the Windows Live services, and he wrote a great paper about a lot of scalability and fault tolerance patterns, which is nice to read also. And my personal favorite, again, Andrew Tannenbaum, his book about distributed systems. This book is pure magic. I've got this book for a lot of years meanwhile, and whenever I find something which is completely new for me, I say, I'm absolutely sure that Tannenbaum cannot have written anything about that. I open that book, and magically, there's a whole chapter about that stuff. This book rewrites itself whenever you open it. It's unbelievable. So, but that's standard equipment. If you're dealing with any kind of distributed systems, which we are dealing most of the time with, meanwhile, I mean, when do you have a system which is just running on one node anymore nowadays? And this should be in your bookshelf anyway, this book. And if these chairs were just way too comfy and you slept for the last 50 minutes or something, were sound asleep and feel now very rested and ready for lunch, then just take this one line with you when going out of this talk. It's all about production. So that's what I wanted to tell you. That's basically all I've got. And thanks a lot for your patience. Thanks a lot for your time. If there are any questions, just come down to me, please, because I think that most of you are going to get a head start for lunch now.